Hey guys, it's Miss LeBron, and I am here for our 1:30 Wednesday appointment. If you check out your calendar today, it is May 6, 2020, and we are going to talk a little bit about percent composition and empirical and molecular formulas today. So why am I eating my snack in front of you? Why am I eating some popcorn? Because I wanted to start off by telling you about percentages and about what they do and their role in chemical formulas. So one thing that I wanted to show you is what I was eating, popcorn. So popcorn's an interesting little thing. When you look at it to begin with, it's nothing but this hard kernel, okay? So how does this hard kernel turn into this fluffy piece of popcorn right here? So it's interesting. Actually, the way this kernel turns into this fluffy piece of popcorn is because inside this little kernel is water. Okay, so what I'm going to do is show you today what it looks like to pop one kernel of popcorn. So I'm going to take one kernel of popcorn and I'm going to drop it in a test tube, and that test tube just has a little bit of oil in it. I tried this earlier today and burned up a couple test tubes because the popcorn burned. So we're going to put a little bit of oil in today. So I'm going to pull my hair back. I'm going to put my safety goggles on, and I'm going to show you what this looks like when this kernel of popcorn actually pops. So why does it do that? The reason that that kernel of popcorn actually pops is because you have water inside that popcorn kernel. And when that water gets really, really hot, the water turns from a liquid into a gas, and that gas has nowhere to go except out. So what happens when that water gets hot enough or hits its boiling point in there where it changes from a liquid to a gas is that that popcorn kernel is basically going to explode. Okay? So you can see that we move from this kernel to this fluffy little piece of popcorn. So what does that have to do with percent composition, which is what we're talking about today? Actually, a lot. One lab that you would do if you were in your classroom, or if we had more time, would be that I could actually pop that popcorn and tell you what percentage of this popcorn kernel was water. And you can do that by a simple mathematical formula, simply by looking at percentages. Because whenever you look at a percent of anything is always going to be a part of something over the whole times 100. So my math people are getting excited today because I'm talking about math and percentages for them. So the way we're going to find the percentage of a formula, or the percent composition of a formula, just how you would find the percent composition of water in that popcorn, is you take the part, you divide it by the whole, and you multiply it by 100. Now that part and whole can be in any unit as long as they're the same. Today we're going to focus on percent by mass. You could do percent by volume. If you were calculating the percentage of red M&Ms, you could do percent of M&Ms. Okay, so your units can be anything as long as they're the same, and as long as you can get a part of that quantity and the entire thing of that quantity. So we're going to be looking at chemical formulas today and calculating what percentage each element makes up in that chemical compound. So grab your calculators. We're going to be doing a lot of math the rest of our time together. And grab your periodic table because you're going to need that too. So our first question comes up, what is the percent composition of magnesium oxide? When it asks you the question, what is the percent composition? That means what is the percentage of each element? So I want to know what percentage of this compound is Mg and what percentage of this compound is oxygen. So we're going to calculate that. And we're always going to be nice and tidy with our work, and we're going to show our work. So the first thing that we're going to do is list our elements in a compound. I know that the elements that make up magnesium oxide are magnesium and oxygen. So I'm going to put a little dash. I said we're going to do percent by mass. Do you remember last week where I told you to find the mass of any element? Hopefully you pulled out your periodic table. Periodic table is where you're going to find the mass of any element, and that's always that bottom decimal place number down here at the bottom. We're going to go to 2 decimal places today. So I'm going to find magnesium, which is atomic number 12, and it tells me that that mass is 24.31 grams per mole. So I'm going to come over here and I'm going to list that weight as 24.31. I'm going to do the same thing for oxygen. If I walk over here and look at oxygen, I see that that mass is 15.999, and for ease, we're going to round that up to 16.00, because that third 9 is going to round us up. So the part of this compound that is magnesium is 24.31. The part of the compound that's oxygen is 16. But what other piece did I say that you needed if you were solving for percentages? You didn't just need the part. What else did you need? You needed the whole. So we're going to add these 2 numbers together. So pull out your handy-dandy calculator, and I'm going to say 24.31 plus 16, and that's going to give me 40.31. But I still have not figured out my percentages yet. What did I say the formula was for a percent? In order to get a percent, you take the part, you divide it by the whole, and you multiply it by 100. These are our parts. So we're going to take each part, we're going to divide it by the whole, which was 40.31. So we're going to divide each one by 40.31, and then we're going to multiply them by 100. So you're basically working 2 math problems at the same time. So if I look at the first one, I'm going to say 24.31. I'm going to divide that in my calculator by 40.31, and then I'm going to multiply that by 100. And that gives me, to 2 decimal places, 60.31% of this compound is magnesium. So remember, we don't want to leave any numbers out there without units. So on the end of this, I'm going to put percent magnesium. Now I need to find the percent oxygen. There's 2 ways to do this. I can either work this entire math problem the same way, 16 divided by 40.31 times 100, or there's a shortcut if this is your last one. What should all of these percentages add up to be? What is a whole? A whole of anything is 100%. So the other way that I can work this is I can say 100 minus 60.31, and that's going to give me 39.69% of this compound is oxygen. Do yourself a favor and do your teachers a favor. They always want you to circle your answers, so make sure that you circle or highlight your answers at the end. All right, so let's try another one. Exact same process. Calculate the percent composition of iron 3 oxide. Do you remember in week 1 when we did reactions, I said you're about to have a really bad time if you can't take a name and turn it into a formula. This is another example of that. You have to be able to write the formula for iron 3 oxide. We know that iron is Fe, and I tell you that it's iron 3, which means that it has a positive 3 charge. Oxide is O. You go look at your periodic table, that's in group 6A. And we said week 1 that anything in group 6A, if you look back here at the very top, had a charge of -2. So we're going to take that -2, and again, this is a review from week 1. We're going to put that number on top of oxygen. Now we're going to crisscross our charges, bring the 3 down here, bring the 2 down here, and we get the formula for iron 3 oxide is Fe2O3. So now that we have our formula, we can start working this problem. We know that our compound consists of iron and it consists of oxygen. But this is a little different than the last problem. How many irons do you have here? You have 2. You have 2 irons. So I know I have 2 irons. How many oxygens do you have? If you look right here, your subscript for oxygen is 3, so you have 3 oxygens. Now, let's go get the weight of these things. So let's go look at the periodic table. We're going to find iron first. Iron is right here, atomic number 26, and we see that that number is 55.85. So I'm going to write 55.85. but I don't have 1 iron. This time I have 2 irons. So I need to multiply by my 55.85 by 2, which means my total weight of iron is 111.70. Well, now let's do the part that's oxygen. I have 3 oxygen, and we just looked up oxygen a minute ago, and we found that it was 16.00. But remember, I don't have 1 oxygen, I have 3 oxygen. So you need to multiply that number by 3, and that's going to give you 48.00. These are my parts. How do you get the whole? To get the whole, you just add them together. So I'm going to say 48 plus 111.70, and that's going to give me 159.70. But you're not done. All you've done so far is you've gotten your parts and you've gotten your whole. So how do you get your percentages? You divide part over whole times 100. So I'm going to take my part, I'm going to divide it by my whole, which is 159.70, and I'm going to multiply that by 100. So I'm going to take 111.7, divide it by 159.7, and multiply it by 100. And that's going to give me 69.94% of this compound is iron. 2 ways you can get the oxygen. Either the exact same process, if you like that routine, part divided by a whole times 100, or I can just subtract the number I just got from 100%, and I get 30.06. So that tells me 30.06% of this compound is oxygen. Circle or highlight your answers for your teachers, and that's all there is to percent composition. You just take the part over whole and multiply it by 100. So let's talk a little bit about how we get these formulas. Let's talk about empirical formulas and molecular formulas. An empirical formula is the smallest whole number ratio of atoms within a compound. The molecular formula is the true number of elements in a compound. So when we look at this formula, H2O2. H2O2 is hydrogen peroxide. There are 2 hydrogens and there are 2 oxygens. That's a molecular formula. It's not an empirical formula. An empirical formula cannot be reduced. So if I have common factors of 2 and 2 here, what can I divide everything by to reduce this? I could divide everything by 2, which means my empirical formula for hydrogen peroxide would be HO. Now, if we look at the next one, what is the empirical formula for C6H12O6? What is your common factor there? What can you divide everything by to reduce it in its most reduced form? I could divide everything by 6. And if I divided everything by 6, I would get that my empirical formula is actually CH2O. So remember, we don't write ones. Ones are understood. So this is how you go from a molecular formula to an empirical formula, but we're actually going to figure out how to calculate those things today based on some percent composition data. Write these steps down. I'm all about steps. The first step in the problems that we're about to do is just like any problem we've done the entire last 4 weeks, is you write down your givens. The next step, and these will make sense once we get into a problem, is you change the percent to grams. Then you're going to do what we did last week. You're going to change grams to moles. You're going to divide everything by the smallest number to put it in its most reduced form. And then you're going to write your formula. So percent to grams, grams to moles, divide by the smallest, multiply till whole. That's a little rhyme to help you remember this. So let's look at an example. What's the empirical formula if you've got a compound that I know chemically contains 40.05% sulfur and 59.95% oxygen? So we know this from chemical testing, but we may not know what the formula for that is yet. So the first step was write down your givens. And my givens are 40.05% sulfur and 59.95% oxygen. So the first step was write your givens. Check. The next step is change percent to grams. So what do I mean by change percent to grams? I mean we are literally going to change this percent sign to a gram sign. Let me erase that so it's not so messy. So we are literally going to change that percent sign to a gram sign. So now I have 40.05 grams of sulfur and 59.95 grams of oxygen. So I wrote my givens, I changed percent to grams, and the reason that we're able to do this is because we're assuming that we have 100 grams of this substance, which would make these percentages true. So the next step was change grams to moles. This is what we did last week, so go look back at your notes from last week. The first step was you put an X and a line. You put the unit that you want to cancel on the bottom. So if I have grams of sulfur on the top, I'm going to have to put grams of sulfur on the bottom. Remember, last week we said that there were two conversions that you could use. One of them was 1 mole of anything is 6.02 times 10 to the 23rd particles. It was called Avogadro's number. And then the other one, the one that we're about to use, is 1 mole of anything has its molecular weight in grams. And you learned that that number comes off the periodic table. That's that weight that we just looked at a minute ago. So we're going to go from grams to moles because the step said change grams to moles. When we look at that conversion, we know that the number 1 needs to go with moles. And grams, we learned last week, comes from the periodic table. So if I go look at sulfur, which is number 16, I see that the molecular weight is 32.06. So on the bottom, I'm going to put 32.06. I'm going to do the same thing for oxygen. I'm going to change it from grams of oxygen to moles of oxygen. I'm going to put a 1 with mole, and grams comes off the periodic table. We've done oxygen a few times today, and we see that he's 16.00. So I'm going to cross out the units that are on the top and the bottom. I have grams of sulfur and grams of sulfur. That's going to leave me with moles of sulfur, which is what I wanted. I have grams of oxygen and grams of oxygen, which is going to leave me with moles of oxygen, which is what I wanted. So we're doing the step on those steps that I just showed you a minute ago, which was changing grams to moles. So we're on step number 3. So I'm going to plug this in my calculator. Don't forget if it's on the top, you multiply, and if it's on the bottom, you divide. So I'm going to say 40.05 divided by 32.06, and that's going to give me 1.25. I'm going to do the same thing for the bottom. I'm going to say 59.95 divided by 16, and that's going to give me 3.75. Now go back to your steps. What did your steps say to do next? We did change gram to moles. The next thing is divide everything by the smallest number. What's smaller, 1.25 or 3.75? 1.25. So we're going to divide everything by 1.25, and that's going to give me 1 and 3. That gives you the whole number ratio of what these elements are going to combine to form in this compound. So what this tells me is that I'm going to have a formula that has 1 sulfur, and I'm going to have a formula that has 3 oxygens. So that formula is going to be SO3. 1 sulfur and 3 oxygens. Okay? Let's try one more of these. Calculate the empirical formula of a compound that contains 48.64 grams of carbon. They already had it changed to grams for me, so that's good. 8.16 grams of hydrogen and 43.20 grams of oxygen. So the first step is percent to grams. That's done. The next step is grams to moles. So on the bottom, I'm going to put grams of carbon. On the top, moles of carbon. This is 1. Carbon on the periodic table is 12.01. And we're going to cross out grams and grams of carbon, and I'm left with moles of carbon. So that's going to give me 48.64 divided by 12.01, which is 4.05. Now I'm going to do hydrogen. Grams of hydrogen goes on the bottom. On the top, we have moles of hydrogen. This is going to be 1 mole and 1.01 grams of hydrogen. We're going to cross out grams and grams, and I'm going to say 8.16 divided by 1.01. And that's going to give me 8.08. I'm going to do the last one, which is grams of oxygen to moles of oxygen. 1 goes with mole. Grams of oxygen is 16. So I'm going to say 43.2 divided by 16, which gives me 2.7. The next step was divide everything by the smallest. The smallest out of these three is 2.7. It's going to give me a 1 there. So 4.05 divided by 2.7 gives me a 1.5. And then 8.08 divided by 2.7 gives me a 3. Have you ever seen a formula that says C1.5H3O? No, you haven't, because these things have to be written in small whole numbers. And I can't just round that 1.5. So I got to multiply that 1.5 by something that's going to make it a whole number. So if I multiply anything that ends in 0.5 by 2, it'll give me a whole number. So this is actually going to give me a 3. But mathematically, whatever you do to one of the variables, you need to do to all of them. So if I multiply one of them by 2 to make it a whole number, I'm going to need to multiply all of them by 2 to make it a whole number. So this is going to give me a 6, and this is going to give me a 2, which means my formula is going to be C3H6O2. All right, so let's look at one more of these, and I'm going to go through the next one pretty fast. We're going to go from empirical formulas to molecular formulas, which is the non-reduced form. Same steps. You find the empirical formula first, then they have to give you a mass in there. They have to tell you in the problem how much 1 mole of this stuff weighs. You're going to take the mass of whatever formula you just calculated. So for example, we did C3H6O2. You're going to add up 3 carbon, 6 hydrogen, and 2 oxygen. You're going to get its mass, and you're going to divide the mass that they gave you by the mass that you're given to get the ratio of what you need to multiply that formula by. So let's work one really quickly, and I'm going to go kind of fast on this one because this is a review. So I have a compound that contains 40.68% or grams of carbon, 5.08 grams of hydrogen, and 54.25 grams of oxygen. And I tell you in the end, whatever formula you get has to weigh 118.1. So really quickly in my calculator, I'm going to change grams to moles. Show your work. I'm going to do it in my calculator. 40.68 divided by 12.01. That's going to give me 3.39. 5.08 for hydrogen divided by 1.01. And again, I'm just skipping a few steps here to get us through on time. Then I'm going to take 54.25 divided by 16, which is oxygen, to give me 3.39. I'm going to divide everything by the smallest, which is going to give me 1, 1.5, and 1. And we just found out you can't have half numbers, so we're going to multiply everything by 2. And we're going to get that our empirical formula is C2H3O2. I told you the next step was to get the weight of this, all right? So we are going to get the weight of 2 carbons, which is 12.01 times 2, plus 3 hydrogens, which is 3.03, and 2 oxygens, which is 16 plus 16, which is 32. So this thing should weigh 59.02 grams per mole. I told you in the problem that it needs to weigh 118.1. So I'm going to take that 118.1, I'm going to divide it by the mass that I got, which was 15.02, And that's going to give me a whole number of 2, meaning that my molecular formula for this was going to be C4H6O4. So you take that 2 and you're going to multiply it by everything that was in your empirical formula. I know that that one was super fast. Make sure you work a lot of examples of these because they're math, and working more problems is going to help you get through these problems. Next week, again, bring your calculators and your periodic table. We're going to be talking about stoichiometry. I hope you guys have a great week. We will see you next Wednesday at 1:30. Have a good one.